Welcome back! In the previous lessons, we have designed and optimized a hardware architecture for our Smith-Waterman algorithm using SDXL. All the previous tests has been performed targeting the same FPGA device, based on Xilinx Virtex-7 FPGA. Now, we will try to test our architecture on a different architecture, based on Xilinx Kintex UltraScale FPGA. This FPGA board features two physical memory ports with the DDR, allowing us to read in parallel query and database from the memory. Let's see how we can specify, with very little effort, this specific behavior to SDXL. The first operations we need to perform is to modify the interface of our kernel with the memory. We need, in fact, to bundle our three ports in three different GMEM positions. Now, GMEM here is just a name that we will then use in our makefile when we will perform the port mapping step. Awesome! Let's now open the makefile. The first thing we have to do in our makefile is to specify that we want to use a different target device. We want to target, in fact, the KU3 with 2 DDR and DSA version 4.0. When specifying the flags for the kernel, we need to map the bundle specifying the memory interface pragma of the kernel with the physical port of the device. In our architecture, we are mapping GMEM0 to the M00 AXI port and GMEM1 to the M01 AXI port so that we can read in parallel both the query and the database. Finally, we are mapping the direction matrix bundled to GMEM2 to the M00 AXI port, so that we can send back the results on the same port where we read the query form. Great! Now, we are missing only one thing to do here. We need to specify this memory mapping in the host code too. Let's come back to SDXL and change the target device to the KU3. Notice that this operation is not necessary here, as I am building the system using the makefile flow. In the host code, we need to define three external pointers, one for the input query, one for the input database, and one for the direction matrix given in output. Now, the external pointers are defined as a struct of three elements. The first one, flags, holds the memory bank where we want the buffer to be sent or received, while the other two fields, obj and param, can be easily set to null and 0. Once we define the query to be sent via the DDR bank 0, the input database to be sent via the DDR bank 1, and the direction diagonal to be received via the bank 0, we need to specify the CLMEM_X pointer Xilinx flag, as well as the host pointer, that in our case is the external pointer, in each of the CL_create_buffer API. Awesome! Now everything has been specified. We just have to start building the architecture and then test the final architecture. As for the previous example, I have built my Smith-Waterman with a query size of 256 and a database size of 256, 65,000 and more than a million elements. Let's now check its performance. For this first example, with query equal to 256 and database equal to 256 characters, we get 0.047 milliseconds, resulting in more than 212 giga operations. Let's see what happens increasing the database to 65,000. (0.42 milliseconds. That is 3,000 giga operations. Wow! Finally, with a database size of more than a million, (7.45 milliseconds and almost 2,800 giga operations. Fantastic! This kernel is able to get performance slightly higher than the one on the Virtex-7, as it has more memory bandwidth. Checking the performance on the roofline model, we can notice that we are matching the performance predicted by the model. And as we are in the memory-bound part of the chart, memory bandwidth is the limiting factor for both our architecture. Great! All the optimizations applied so far allowed us to get a super performant hardware architecture for the Smith-Waterman algorithm for 2 target devices. We use the roofline model to predict system performance and drive the optimization process, designing the hardware architecture using Xilinx SDXL and Vivado HLS.